Okay, great. What's up, y'all? How's it going? Okay, good. Can y'all see? Should I close these lines awkwardly? Yes? Okay. That good? Great. First things first, do we have any housekeeping things, logistical things? Any questions of that? Sure.
How do you stop yourself from spending hours on coding one block?
Oh, When you find the answer to that, let me know.
Okay.
But
that happens, not just me.
yeah, especially because it was ggplot for the homework. And the spiral of wanting the graph to look a certain way will always come and get you.
Okay.
So I would just say set a timer. Any other questions? Okay. I started looking at the homeworks and the peer reviews today. I haven't finished grading them all, like assigning grades for them. It's okay to just give someone a 2. Okay. A lot of people are like, I don't know, maybe like a 2.5. Just give them a 2. It's okay. It's a credit, non-credit class. If you get a 2 every week, you will pass. It'll be okay. Yeah, so I don't want to see any more 2.8s. It's okay. Oh, I did have another logistical thing. I am getting my wisdom teeth out on Friday. I know. I'm gonna become an adult. But I don't know what the recovery time is like. I don't think we have any School of Dentistry people in here. So I'll let you know if I feel like lab should be online on Monday. But there will still be lab, but it might be online. Hello. All right, great. It's week 3. We're getting into a lot of what our coding turns out to be for social scientists, which is cleaning data sets, manipulating things, and summarizing large swaths of data to 2 digits of information that's critical to policymakers. Let's get started. The theme for week 3 is death to spreadsheets. Today, we'll be talking more in depth about dplyr, a package that does in R just about any calculation that you've tried to do in Excel, but more transparently, reproducibly, and safely. Don't be the sad research assistant who makes headlines with an Excel error like this person. I'm sure we've heard about a lot of errors in cells regarding data in the last year or 2. We're going to get started by talking about modifying data frames with dplyr. But first, pipes. Actually, I'm going to hide this. Okay. We got introduced to pipes last week, and we only used them for one particular reason. I want to talk about the other benefits of this sort of syntax while you use R. So dplyr uses the magreader forward pipe operator, usually called simply a pipe. We write pipes like % greater than %. You can also, after you've loaded dplyr, just use Control-Shift+M. Or if you're an Apple user, that swavy thing, Shift-M. What a pipe does is it takes the object on the left and applies it to the function on the right. So object, pipe, function argument equals y, is the same as function object as an argument equals y. In this case, while there's only one pipe, these are virtually identical, and it doesn't seem that much more beneficial to use pipes. Today, what I want to motivate is that piping is incredible and helps us for a lot more complex tasks than this example here. Throughout, I will read aloud the pipe operator as and then. So just keep that in mind when you're reading a chunk that has chained pipes, and then is your friend. An example here, let's say we load the dplyr library and the gapminder library, and we'll take the gapminder data and then filter country equals Canada, and then show me the first 4 rows using the function head. This is how we were using it for our ggplot assignment. And one of the strengths here is being able to chain arguments together or chain commands together. Pipes save us typing, first and foremost. They make code readable in a left to right, top to bottom order, and they allow chaining like above. So we're going to use them all the time when manipulating data frames for these purposes. When using pipes, pipes are clear to read when you have each function on a separate line. It'll be inconsistent in these slides in a couple places, and I'll point them out. And it's due to the size of the slides. That's not how I would put it in a script. So an example would be, we take these data and then do the first thing with this value, and then do the next thing using that value, and then until eternity. So stuff to the left of the pipe is passed to the first argument of the function on the right. And you might be saying to yourself, I didn't know they were ordered. How am I supposed to know that moving forward? If you go to R and use the question mark and then the function to pull up the help pane, the order of the arguments is the order that the function takes the arguments in the help pane. So it'll normally start with if this takes a vector, or this takes a tibble, or this takes a data frame, this takes a list. I'll give you an example right now. In my console, I could say question mark filter. And the first argument, oh, this is for the stats filter, not dplyr filter. The first argument here, this is still instructive, is a univariate or multivariate time series. So if you were trying to pipe something into there and it's not a univariate or a multivariate time series, it might yell at you. Whereas dplyr's first argument is a data frame extension, or a lazy data frame. You can see methods below for more details. Also, if you ever find yourself piping a function where data are not the first argument, use a period, use the dot in data argument instead. For instance, you could say gapminder and then LM for linear regression, pop by year, comma, data equals dot. But if you just said gapminder and then pop by year, the function would yell at you. So a little bit about using pipes to make objects. When creating a new object from the output of piped functions, place the assignment operator at the beginning. So you want to think about it like you're mixing a recipe. that you already have in mind that you're going to come out with a cake, and then you're going to start putting together all of the ingredients. For instance, here we will create a new object, lm_pop_year. We will assign it the gapminder data, and then filter to values in the continent column, which equal Americas. And then we'll run a linear regression by population or population by year, data equals dot. And so no matter how long the chain of functions is, assignment is always done at the top. Note, this is just a stylistic convention. If you prefer, you can do assignment at the end of the chain. I do not highly recommend doing this. As when you return to your code, you'll often find that you're only interested in what this chunk produces and not necessarily how you got there every time.
So can you just go over again what you're saying? Yeah.
Sure. So the question was, can I explain why data equals dot when gapminder was called earlier in the chain? So the gapminder data is being passed along all of these functions. And then in the last section, in order for the last function to know what's being passed to it, we say data equals dot. This tells the last function where the data needs to go. The gapminder data that you've been manipulating.
Would you also, would it just be redundant, but would it work to write gapminder in place of dot still?
No, because it's not the gapminder data anymore. It will have been manipulated partway through the chain. If you don't put data equals dot, it will pass the things that's being piped. So the gapminder data that you've now filtered and is now going to this linear regression to the first argument of the linear regression. And the first argument of linear regression is actually your outcome variable. So it would throw back a error because you're giving it a data frame when it wants just a column. That's exactly right. The reason that it's dot is something you can look up. It's an ancient secret. I don't feel like a lot of the folks in this class want to fight it. Just believe me that your data is now dot, and we'll all go home happy. I introduced filtering rows or subsetting using the dplyr package last week. And an example would be we create this Canada object by assigning it the gapminder data, and then we filter to values in the country column that are equal to Canada. And so when we look at this, we just get rid of all of the rows that were not equal to Canada. I'm pretty comfortable with that. Do we have any questions with filter so far? Great. Another operator that you will see yourself using a lot when it comes to filtering things is this % and % operator. I had a question during lab on Monday. What is this called? And so I thought, I don't know. Let me check. And I still don't know. I checked. I don't know what this is called. I just always called it % and %, and I know what it does. So the common use case for filtering rows in some set is how you would use % and %. We use it like the equals equals. So we make a logical expression, but for matching any element in a vector on the right. So let's say we make a vector called former Yugoslavia and assign it the names of countries from former Yugoslavia, like Bosnia and Herzegovina, Croatia, Montenegro, Serbia, and Slovenia. Now we could say, let's make an object called Yugoslavia, and assign it the Gapminder data and then filter country percent and percent the vector former Yugoslavia. And so now this will match any of the elements in our vector in that column. This is a really wonderful tool. Note, I'm also showing how it works with this 3x6 table here. And I use the slice function. The slice function will come up a couple times for examples in this lecture. It works like head or tail in that it shows you specific rows, but you can just grab some in the middle of your data frame instead of just the top or the bottom. So here I've specified that I want rows 12 through 14, and I got just those in my data frame. Question?
How come when assigning the object form to the copy and you're telling it the country, how come you don't have a data set?
These are just the character strings. It's like when we were doing this with Canada, where you're just saying Canada. But we want a list of those things in a vector so we can match all the elements.
You get the same, like another way to do the filter percent, like do country equals again, or this or that or that. It's just a simpler way. You're just creating a vector.
Yes.
First, and then putting that in for a simpler second.
Exactly. And doing it this way by separating it into a vector and then doing percent and percent makes it so that if you're like, you know what, I want former Yugoslavia and also Colombia for some reason, you can just change the vector and then run the code again and it will know. Question in the back. Let's see. That was because I know the data set and I know that there are 12 years in the data set, and I wanted to be able to show that I did have more than one country. So I needed at least the 12th row and then maybe a couple more. Right. Yes. Did I see another hand? Okay, no worries. You are like 10 slides ahead of where we're at. So you're on it, you're good. Okay. I will be presenting a lot of different functions today in relationship to our manipulating and summarizing data. This begins the train of cool functions. One of which is called distinct. You can see all of the unique values in your data for combinations of columns using the distinct function. For instance, you could say Gapminder and then distinct continent and year. And the output will show a table with each of the unique pairings of those two columns. This is really great when you want to know how many different combinations of things that I have or how many duplicates I have of things. But don't use this to deduplicate your data set. Don't use distinct to deduplicate your data set. I'm telling you. Part of the reason is that the way that distinct works is that it reads down your data frame and it says this first combination, this first row, has a unique answer for the continent and a unique answer for year. And then it jumps down to the second row and it tries to do the same thing again. When it does that, it means it'll only grab the first time that there's a unique pairing. And so oftentimes when you deduplicate things, you don't necessarily want the first unique pairing. Sometimes you want the third or the 11th or the 28th. And so I don't recommend deduplicating with distinct. Question.
I have a troubleshooting question.
Okay.
So every time I do math like this, it gets mad at me and says that content isn't an object.
Okay.
Am I missing loading gapminder somewhere for it to like not pull from the data set?
I think so. My thoughts are that perhaps in your markdown that you have loaded gapminder and that it is below the function call. But it should be one of the first things so that anytime anything that gets pulled out of that package, the package has already been loaded for the markdown. You just need to have it in the first chunk because markdowns read things top to bottom. And so you want your packages and your data in like the first chunk. And that way it knows where to look for things in the later chunks. Question?
Since we're talking about loading these packages within like the R markdown files, I was wondering if there's some separate process for making sure that those don't load the final HTML. Because when I was loading like gapminder, dplyr, stuff like that in my R markdown document, it always printed out the chunk despite the fact that I had that echo was false.
Mm-hmm.
Is there some separate process that you need to go through?
It printed out the chunk even though echo was false. I would like to see that afterward. Yeah. Okay. Because I have a couple of theories, but there are a lot of words that maybe wouldn't make sense immediately. About distinct. So distinct also drops unused variables. You'll notice in our last example, it was just the pairing that we wanted to know the distinct combinations for. In this one, there is a method to keep them. Note the default behavior is to drop all unspecified columns. If you want to get distinct rows by certain variables without dropping the others, use distinct dot keep underscore all equals true, and it will keep those other columns for you. This slide's mostly in there because people ask me about it, but I don't get a lot of terrible use out of dot keep underscore all equals true. Another function is sample underscore n. This is for sampling rows. We can also filter at random to work with a smaller data set using sample n or sample frac. In this example, I set.seed 789, which I always do. This set.seed allows you to make random draws repeatable on other people's machines. Our example here, let's say we take that Yugoslavia data set that we made earlier, and then sample n size equals 6. So we're going to get 6 rows back, and replace equals false. So we're not going to put rows back after we've sampled them. Here we have a 6x6 data frame with Serbia 92, Serbia 2007, et cetera, et cetera. If you, on your own machine right now, were trying to create this, and you didn't set.seed 789, there's an infinitesimally small chance that you would get this same 6 rows. Whereas if you did set.seed 789 and ran it one time, you would get these exact same 6 rows. This is really great when, I don't know, you're doing some sort of cross validation technique, or you're doing some sort of specific sampling procedure, and other people on their machines that you're collaborating with also need to have the same data. So we use set.seed to make all random numbers in a file come up exactly the same each time it is run. You can read the details in set.seed if you like your brain to hurt. There's a lot of really weird explanations of why set.seed works in there. Check it out if you have time. On sorting, there's the function arrange. Along with filtering the data to see certain rows, we might want to sort it. So let's say we take the Yugoslavia data and then arrange it by year and then by descending order of population. So what we'll get is, you'll notice in the year column, it starts with 1952, our farthest back in history year. It leads up to 2007, I think. And then also within that year, it's in descending order of population. Very neat. Also, arrange knows the data types of the things that you're arranging. So you can also arrange characters by alphabetical order. Question?
So I see that you don't specify ascending for the year. It's not because ascending is just kind of like the default direction.
That's exactly it. Note also that the argument for descending is its own function. These are called helper functions and are very common in the tidyverse, especially when it comes to manipulating data. So we could even leave pop empty there, and it would still produce arranged by year, but it would make it in descending order for year. I would say play around with it, and you'll quickly see how it works. On keeping columns, there is the select function. And I'm sure I brought it up a bunch of times. The dplyr likes to flex about masking over select as one of their things. It's because select for dplyr is very, very, very important. Not only can we limit rows, but we can include specific columns and put them in ordered list in the order listed using select. So let's say we take the Yugoslavia data and then select country, year, and pop, and then show the first 4 rows using the head function. And note, now we have country, year, and pop in that order, and we have dropped the other columns. This is a really strong function. It can get a lot done for you. You can also drop columns in specific using select. We use the minus sign to achieve this. So let's say we take the Yugoslavia data and then select minus continent, minus pop, and minus life expectancy. And then show me the first 4 rows of that. And what we'll get are country, year, and GDP per capita. So we can also drop columns that we don't want anymore. Question?
Can you also do vectors in here, like if you want to drop a ton of columns or like
Yes.
a ton of columns?
Yes, you can. And that's the way I would recommend doing it. Especially when you have something like a census data set and you want to keep just like all of the B100 ones. It's way faster to do it that way. Question?
Don't there like those loops? So let's say I want to take like the first 3 letters of the first 4 letters of each and everything else that fits into the other still have the words.
I'm not sure if filter has its own helper function for that. Select does. Yes, and week 8, I think, when we do text stuff, I'll show methods about how to do what you're describing. But if between now and then you have a use case, just send it to me and I'll help. So a little bit about helper functions for select. Select has a variety of helper functions like starts with and ends with and contains. Or it can be given a range of contiguous columns by using something like the starting variable colon the ending variable. See question mark select for details. These are very useful if you have wide data frames with column names with the following a pattern or ordering. So here we have the Denver Youth Survey. This is a data set that has 6 rows and 292 columns. And one thing you could do is say the Denver Youth Survey and then select starts with the word married. And then you would keep only those columns that start with married, like here. Alternatively, you could say Denver Youth Survey and then select ends with the number 18. And we'll keep only the columns that end with the number 18. Contains works very much the same way, but you would be able to specify things that are just within the column name somewhere, not necessarily in the front or the back. A helper function that only recently came to the tidyverse, like maybe a year and a half ago, is called where. It's especially useful for select is where, which can be used for selecting columns based on functions that check column types. So we could say, take the gapminder data and select where the columns is.numeric. Is.numeric is a function that checks whether or not things are numbers or some other data type. So take the gapminder data and then select where is.numeric, and then show me the first 3 rows. And then we will keep only those 4 columns that are numeric values. So we no longer have continent or country. You can also do this for the other type of variable that's in the gapminder data set, a factor. So take the gapminder data and then select where is.a factor, and then show me the first 3 rows. And we only get those 2 columns. Question in the back. Oh, yes, that's what this picture is that I put in here. It's from the Denver Youth Survey. And I didn't want y'all to have to load it in, but I also didn't know a freely, easily used data set that would show off how this works. Of course. We can rename columns with select, but it drops everything that isn't mentioned. So I only use this in very small use cases. Let's say I want to make a table that only has 2 columns, but I want the column name to be really cute. So for instance, we could take the Yugoslavia data and then select life_expectancy equals life exp, and then show me the first 4 rows. And here our table name or our column name has changed. This is not our favorite way to do things because it drops all of the other columns. Instead, the safer way is to rename columns with the function rename. So rename does exactly what it sounds like. It renames variables using the same syntax as select without dropping unmentioned variables. So we could take the Yugoslavia data and then select country year life expectancy and then rename life_expectancy equals life exp, and then show me the first 4 rows. And we'll see that we still have country and year, but life expectancy is a little bit more legible. We could, but then there would be 6 columns on this slide, and then it would go a little bit over to the edge.
Oh, so like,
Right. A note about column naming practices. Good column names will be self-describing. Don't use inscrutable abbreviations to save typing time. RStudio's auto-completing functions take away the pain of long variable names. You can just hit tab while writing code to auto-complete objects that have already been created. or column names that are already available. Valid naked column names can contain upper or lowercase letters, numbers, periods, and underscores. They must start with a letter or period and not be a special reserved word. Special reserved words are things like true, false, if, else, next, skip. There's a lot of them. But you'll run into them all more or less in this class. Note that names are case sensitive. Capital Y year and lowercase y year are not the same thing. You can include spaces or reserved words if you put backticks around the name. Spaces can be worth including when preparing data for, say, a ggplot2 or a pander, since you don't have to rename axes or table headings.
Question actually quickly going back to the rename.
Sure.
If you want to rename a bunch of variables,
Mhm.
Do you have to do rename separately, or can you put like all of the new names in front of the equal sign and all the old names after the equal sign?
I don't know if you can do two vectors next to each other on the other sides of the equals. I haven't tried though. I would put a comma after exp and then hit enter. I'll give you an example. Like this.
Oh, okay.
And part of that is I'm not sure that R is terribly appreciative of a vector as the first part of an argument to a thing that it's equal to after you've already piped in something else. Here's an example of a column name with spaces in it. We can load the library pander, take the Yugoslavia data, and then filter country equals Serbia, and then select year and life expectancy, and then rename year with a capital Y and life expectancy in backticks with a space in between life and expectancy. And then give me the first 5 rows and then put it in a nice little pander table. And great, we have a space there. It looks great. It's still pander. Install that package as pander. Cool. Next, we can create new columns. This is how you make money as an RA. I'm joking. I mean, it kind of is. You can create new columns using the function mutate. The reason it's called mutate is .com era shenanigans. You don't have to think about it too hard. Mutate makes new columns. In dplyr, you can add new columns to a data frame using mutate. For example, we can take our Yugoslavia data set and then filter country equals Serbia, and then select the year, the population column, and life expectancy column, and then mutate pop underscore million equals pop divided by a million, comma, life expectancy past 40 equals life exp minus 40. And then show me the first 5 rows of this. And we'll see that we've created a new column. Here, 6.86 in the pop million column is mirroring this 6.86 million-ish number here. And life expectancy past 40 is 18 here and 58 here. You can create multiple variables in a single mutate call by separating the expressions with commas. I like to do comma and then enter so that I can see all of the columns being made in one mutate call. As another practice thing that's to myself, if I'm going to be creating multiple columns based on one particular variable, I will make a new mutate call for that and pipe it into another one that mutates based on a different variable. But that's just for legibility for me. A common function used in mutate and in general R programming is if else the function. There are other if else kinds of statements. We're talking about if else the function. It returns a vector of values depending on a logical test of some kind. The format of it is that you use the if else function, then there's a test that you specify the test as something like x equals y. And then if x does equal y, which is a yes, return this first value. And if it equals no, return this second value. I know I'm talking a little bit in abstraction. I'll show you an example in a second. So the output from if else, if x equals y is, if it's true, you'll get the first value. False, you'll get the second value. And if it's NA, if it's missing, you'll receive an NA. And this is because you can't test for NAs with an equality. We don't, it's maybe a little bit outside of the scope of the class about why that is in particular, but we'll cover that some more. So here's an example. We'll make an example vector, assign it these elements, the number 1, 0, NA, and -2. And then we say, if else, example vector is greater than 0. So here's our test. And then if it's true, return the word positive. And if it's false, return the words not positive. And what this will return to us is 1 greater than 0? Positive. Is 0 greater than 0? Not positive. Is NA greater than 0? I don't know. It's missing. It's an NA. Is -2 greater than 0? Not positive. So this is a very strong tool when used, especially in conjunction with mutate. Let's look at some examples. So let's take the Yugoslavia data and then mutate short country equals if else country equals Bosnia and Herzegovina, return B and H. Excellent couple of letters there. If false, as dot character country. And then select country, short country, year, and population, and then arrange by year and short country, and then show me the first 3 rows. So here is our table. We'll see that in our country column, there's Bosnia and Herzegovina here, but in short country, we have B and H. For Croatia in our second row, it does not equal Bosnia and Herzegovina, so short country is just equal to Croatia. So let me talk a little bit about how you would read this if else within the mutate. You read this as, for each row, if country equals Bosnia and Herzegovina, make short country equal to B and H. Otherwise, make it equal to that row's value of country. So for things where it's false, that is equal to Bosnia and Herzegovina, just return the country column, the value that's in the country column there. This is a simple way to change some values, but retain the others. Note that since country is actually a factor variable in the Gapminder data, I had to use as.character to convert it to a character. That's why there's a little bit of extra function stuff going on there. because if else, yes, so that's what the new column is being created with. So if you'll recall in this example, like I said, pop million is pop divided by a million. The if else here is replacing that pop divided by a million. So this is the thing that's going to produce a new column because it returns new values based on information already in our data set. Yes. So you can put a function here instead of pop divided by a million. Yes, because there's not information from earlier in the chain that's being given to the if else because it's already there. Yes. Okay, we also have the recode function. It's another useful function to use inside of a mutate call. Use recode to change specific values to other values, particularly with factor variables. You can change multiple values at the same time. Note if a value has spaces in it, you'll need to put it in backticks. For example, we can take the Yugoslavia dataset and then mutate country equals. So we're overwriting our original country variable here. Country equals recode our country variable. And then the Bosnia-Herzegovina value, replace it with B and H, and Montenegro, replace it with M. And then show me the distinct country values. And we'll see that now our country variable has B and H, but still Croatia, and M's replace Montenegro, but we still have, we still have Serbia and Slovenia.
So in this example, or in the previous example in our if else, Bosnia has to be in like double quotation marks,
Yes.
but in recode, it only has to be in backtick. Like Montenegro would have to be in quotation marks in if else, but it doesn't need quotation marks in recode.
Yes. And part of that is for ease of use at this stage in the class. We will be replacing recode with a stronger function later. And so the reasons that it's breaking rules that we had earlier is because it is a base R function and not a tidyverse.
Oh.
Question?
Is recode just changing it for this output? Like we haven't gone in and actually changed the like, data set.
Yes, that is, unless we assigned it to the same object. Question? I'm sorry, can you say it again? Yes, in the second case, in this one, I overwrote the column that already existed. So this is like saving to the same column. Whereas in the other one, I've produced a new column. Cool. Great. Next, we have case win. Case win performs multiple if-else operations at the same time. Case when allows you to create new variables with values based on multiple logical statements. This is useful for making categorical variables or variables from combinations of other variables. Let's look at an example. Let's take the Gapminder data and then mutate GDP per capita ordinal underscore ordinal. So we want it on an ordinal scale. This is going to be equal to case when GDP per capita is less than 700, return the word low. When GDP per capita is greater than or equal to 700 and GDP per capita is less than 800, return the word moderate. And when all values of when all other statements are false, return the word high. The way we write that is just by typing true in all caps and return high. So we'll slice to get just a rows 6 through 9 in the data set. And here what we'll see is that GDP per capita ordinal takes on these character values that we supplied, low, moderate, and high, based on multiple logical expressions. Our next function is pull. Sometimes you'll want to extract a single column from a data frame as a vector or as a single value. Pull pulls a column of a data frame out as a vector. For instance, we can take the Gapminder data and then pull the life expectancy column and then show me the first 4 rows. And what we'll actually get as for our output here is a vector with 4 elements. Whereas if we had taken the Gapminder data and then selected life expectancy instead, and then said, show me the first 4 rows, we would still get a data frame that has 4 rows and 1 column. One of our great use cases for pull is inline codes. So pull is particularly useful when you want to use a vector-only command and a dplyr chain of functions, say in an inline expression. In this inline code, the average life expectancy in Afghanistan from 1952 to 2007 was backtick lowercase r. Take the Gapminder data set and then filter country equals Afghanistan, and then pull the life expectancy column, and then get the mean of that column now as a vector, and then round to 1 decimal place, years. We'll produce this output. The average life expectancy in Afghanistan from 1952 to 2007 was 37.5 years. So the mean function in base R can only take a vector input, not a data frame. So this won't work if you said select life exp instead of pull life exp. So that was manipulating data frames with dplyr more or less. Now we'll be talking about summarizing with dplyr. So for general aggregation, we'll use summarize. Summarize takes your columns of data and computes something using every row. Something like count how many rows there are, calculate the mean, compute the sum, obtain a minimum or a maximum value. You can use any function in summarize that aggregates multiple values into a single value. This includes things like standard deviation, mean, or max. An example of summarize in action. For the year 1982, let's get the number of observations, the total population, the mean life expectancy, and range of life expectancy for former Yugoslavian countries. So we'll take the Yugoslavia data and then filter the year equals 1982, and then summarize, and this is going to create columns here. N obs equals n function. Total pop equals the sum of the population column. Mean life expectancy equals the mean of life exp. Range life expectancy equals max life exp minus min life exp. And what this will produce is a data frame with 1 row and 4 columns. One telling us how many observations are in 1982 in the former Yugoslavia dataset, the total population of all the countries during that year, the mean life expectancy, and the range. So these new variables are calculated using all of the rows in the Yugoslavia dataset, but it summarized them down to just one value. Next, and importantly, we want to avoid repetition. One of the strengths of using the tidyverse over base R or data.table is that we don't have to repeat ourselves very often. One helper function available for summarize is across. Maybe you need to calculate the mean and standard deviation of a bunch of columns. With across, put the variables to compute using the vector concatenate function or select syntax, and put the functions to use in a list after. For example, take the Yugoslavia dataset and then filter the years 1982, and then summarize across the life expectancy column and the pop column, and compute in a list average equals return the mean of these things, SD equals return the standard deviation of these things. And what we'll get when we run this is a column or a data frame with 1 row and 4 columns. The life expectancy average, 71.3, the life expectancy standard deviation of 1.6, pop average, and the pop standard deviation. Note, it automatically names the summarized variables based on the names given to lists. This is tremendously powerful. And how quickly it's able to produce all of these things is great. And also note that we have a lot of things going on here, and it still reads left to right. Other things of note here, the tilde lets the summarize across know what function to run and what to return. And the dot says, where should I put all of these things I'm summarizing? One thing you might be saying is, well, that's too many parentheses. I'm looking at a bunch of nonsense. It can get hard to read code with lots of nested functions. Break things up when it gets confusing. One way you could do this is by putting each step on its own line, and it will automatically tab them over. So things that are within one particular function will actually be on the same parallel. Also, RStudio will keep track of your parentheses. If you put your cursor or your caret on the parentheses, it'll show you, it'll highlight the other parentheses that it's attached to. Or you can set rainbow parentheses, which I highly recommend. I can't get rainbow parentheses to print in the slides because it's a little bit too new. but I can show you what they look like. So they are color coded to tell you that this lime color is attached to this one, and this lime color is attached to this one, and this orange one is attached to this orange one. If you go to the link that's in the slides, it'll take you there. Yeah, rainbow parentheses is great. It's also very new, like as in maybe the last 6 months. So continuing about avoiding repetition, there are additional ways to use across for repetitive operations. You could put a helper function inside of yet another helper function and say across everything, and this will summarize or mutate all variables sent to it in the same way. For instance, getting the mean and standard deviation of an entire data frame. So you could say data frame and then summarize across everything list for the mean and standard deviation. I tend to use something like this for, actually, it's the next example. We can also use across where. You'll recall where from earlier, where we said like where is dot numeric. Across where will summarize or mutate all variables that satisfy some logical condition. For instance, summarizing every numeric column in a data frame at once. So we could say, take this data frame and then summarize across where our columns are numeric and give me the mean and standard deviation of all of them. As there, you can also, instead of summarize, put mutate here. And so what I often do is I'll say data frame and then mutate across where is dot character, and I'll make all of my character strings lowercase. I do that for virtually all data sets that I deal with pretty early on.
Write that code out. Like, yeah,
Sure. So I'm trying to think about, I guess we could use the gapminder data set. Hold on. I think that I'm in the wrong section. I'm sorry. I'm going to need to get back to you on that because I can't remember how to do it right off the top of my head right now. I tend to just copy and paste my old code. Our next function is group by. The special function group by changes how functions operate on the data. And most importantly, summarize. Functions after group by are computed within each group as defined by variables given, rather than over all of the rows at one time. Typically, the variables you group will be integers or factors or characters and not continuous real values. If you are an Excel head, this is like pivot tables. A group by example. Take the Yugoslavia data and then group by the year and then summarize the number of countries And here we'll use the n distinct function. Calculate the total population by summing up population, and the total GDP per capita by summing the population times GDP per capita divided by the total population. And then show me the first 5 rows. And here we'll see, because we did group by with the year as our grouping variable, then use summarize, we get 1 row per value of year. And this is just what it's all about in social sciences, right? Group by state, group by whatever. I wanted to talk briefly about window functions. Grouping can also be used with mutate or filter to give rank orders within a group, lagged values, and cumulative sums. You can read more about window functions in this vignette. I highly recommend reading that vignette. It looks a little old-timey. It's written a little old-timey, but it's really good for explaining what all of these things are. But here's an example. We can take the Yugoslavia data set and then select the country, year, and population columns, and then filter for years greater than or equal to 2002. And then we'll group by the country, and then we'll mutate 2 new columns. Excuse me. The first is lag population, which is equal to the lag function. Its first argument will be population, and we'll order it by the year. And the next will be population change, and we'll make that equal to the population minus the lag population. And then show me the first 4 rows. And here what we get is a data frame with 5 columns and 4 rows. For the first 2 rows, we have Bosnia and Herzegovina for year 2002 and year 2007. And note that we don't have answers for this lag pop and population change columns because we don't have a preceding year for that. Whereas in 2007, we can calculate the lagged population and the population change since the prior year. Something also of note in this example is that within the same mutate call, I can point to columns that I made earlier in it. So here we made lag population, and then here we used lag population. Okay, that was summarizing more or less. And now we'll be talking about joining or merging data frames together. My tea got cold. Okay. When do we need to join tables? Let's say we want to make columns using criteria that are too complicated for base R if else or case when. We can work with small sets of the variables and then combine them back into our original data set. Or let's say we want to combine data that's stored in 2 data sets or in separate data sets. Something like local lockdown measures and stationary bike sales. Oftentimes, large surveys are broken into different data sets for each level, things like the household, individual, and the neighborhood, and we'll use joining to connect them back together. So let's talk about the concept of joins. We need to think about the following when we want to merge data frames. Data frames A and data frame B. Which rows are we keeping from each data frame? Which columns are we keeping from each data frame? And which variables determine whether the rows will match? make sure to remember this slide. These are the important steps of joining data frames and are imperative to the way that joining works. Excuse me. So here are the joining types. I'm going to say all of these things, and they're probably not going to stick yet, and that's okay. There are many types of joins. We could, for instance, say data frame A and then left join B. This will keep all of the rows from data frame A matched with data frame B wherever possible, and then it's missing when they're not matched. This will keep the columns from both A and B. We could use data frame A and then right join B. This will keep all the rows from B matched with A wherever possible, and A when not, and keeps the columns from both A and B. There's data frame A and then inner join B. This keeps only rows from A and B that match, but it keeps the columns from both A and B. There's data frame A and then full join B, which keeps all rows from both A and B matched wherever possible, and A when not, and keeps the columns from both A and B. There's data frame A and then semi-join B, which keeps rows from A that match rows in B and keeps columns from only A. And this one's important, I use it quite a bit. Data frame A and then anti-join B. This keeps rows from A that don't match rows in B and keeps columns from only A. For most of the time when you want to do joins, just left join is all you need. A little bit on matching criteria. We say rows should match because they have some columns containing the same value. We list these in a by equals argument to the join. So our matching behaviors that are available to us in the dplyr joins. If we say nothing to by, the match will be using all variables in A and B that have identical names. We can specify a vector by equals variable 1, variable 2, variable 3, and match on identical values of variable 1, 2, and 3, which are columns that are present in both data frame A and data frame B. Or we could say by equals and then make a vector where the first element of it says data frame variable or data frame A variable 1 is equal to a variable in data frame B with a different name. And we can actually specify multiple ones of these. This will match identical values of data frame A variable 1 in the data frame A to data frame B variable 1 in variable or in data frame B, and so on for additional variables. Note, if there are multiple matches, you'll get one row for each possible combination. That's really important. If there are multiple matches, you'll get one row for each possible combination, except when you use semi-join and anti-join. If you need it to get more complicated, break it into multiple operations. Sometimes you will need to break things into 4 data sets and then left join them back together. Okay. Yeah. So now I will introduce the New York City Flights 13 data. We will use this data in the NYC Flights 13 package. So install it and load it. I will join you. Okay. This package includes 5 data frames, some of which containing missing data, which you'll see are shown, their values are shown as NA. It has a flights data frame. These are flights that are leaving JFK, LaGuardia, and whatever the third one is. I've only been in New York for like 2 days. EWR. Newark, New Jersey. That's not okay. So that data frame has flights leaving JFK, LaGuardia, and Newark in 2013. There is an airlines data frame. This is just airline abbreviations. There's the airports data frame, which has a lot of airport metadata. The planes data frame that has airplane metadata, and weather with hourly weather data for JFK, LaGuardia, and Newark. Note these are separate data frames, each needing to be loaded separately. So something like data flights, data airplanes, and data airports separately, and so on. So a few examples of joins. Let's say we have the question: who manufactures the planes that flew to Seattle? We'll take the flights data and then filter dest, short for destination, equals C, SeaTac Airport, and then select the tail number, and then left join our planes data, and then select from that the tail number and manufacturer, join that by the tail number, and then count the manufacturers, and then arrange in descending order. So what we'll get is a data frame with 6 rows and 2 columns, manufacturers in 1 column, and the number of flights that, or the manufacturers of the planes that flew to Seattle. Note, you can perform operations on the data that are inside of functions, such as left join, and the output will be used by the function. So here, we've left joined by the planes data and selected just the 2 columns that we're interested in. But it's also within the same chain that started with the flights data. Question? What's going on with tail num here?
Like, what is it?
I assume that's just like the license plate of airplanes. I don't really know. I'm sorry. Count, this function here, does exactly what it sounds like. It counts the observations by the group that you put here. So this is a short way to say, do like group by summarize observations equals n function. This is a really quick way to do that. And note that it also produces its own column that's just called n. And that's what this n is here. Our join example number 2. Which airlines had the most flights to Seattle from New York City? Here, we'll take the flights data. Question.
Sorry, so when you put in n, it will just automatically always like order things in descending.
No. This n is a column that was produced by the count function.
Oh, okay. So is that already in like data set, or did you like you run options for these stuff?
I would like some more clarification.
Sorry, so the count, the like n column, did you create that, or is that something already like in the data?
That's something that the data, that the count function produces
Okay.
from the data.
Okay.
So it said, how many manufacturers do I have? And it counted all of them.
Oh, I don't know, this is fine.
Yes.
Okay, thank you, sorry.
No, you're good. Example number 2. Which airlines had the most flights to Seattle from New York City? Here we'll take the flights data and then filter destination equals SeaTac and then select the carrier and then left join to the airlines data frame by carrier. And then we'll group by the name and then tally. And then arrange in descending order of n. So here our output looks like 5 rows and 2 columns, where the name are airlines and the columns are, and the other column is n, is the number of flights from that airline that went to Seattle. I'm showing you group by and then tally does the same thing as count in this instance. So it produced this n column, and it was based on this grouping, very similar in setup to count in the previous example. The reason you would want to use tally instead is often when you want to group by multiple categories. While count can handle that, it is easier to conceptualize, at least for me, to do group by multiple groups and then tally. At this stage, like at this part of the chain, the data sets have already merged. Of course. I note here that tally is a shortcut for summarize, and then the function n. It creates a variable n equal to the number of rows in each group. Example number 3. Is there a relationship between departure delays and wind gusts? So here, I'm going to produce a plot. I'm going to load library ggplot2. I'll take the flight's data and then select the origin, the year, the month, the day, the hour, and the departure delay. And then I'm going to interjoin it with the weather data by origin, year, month, day, and hour. And then I'm going to select just the departure delays and the wind gusts columns. And then I'm going to remove rows with missing values. And the way that this works is a little bit counterintuitive, but if you recall earlier, I said that you can't use equalities with an NA. So the way that this works is it says filter, exclamation point, negating something, is not, or filter, negate is.na departure delay. So is.na just tells you whether or not something is an NA. And by putting this exclamation point ahead of it, I said the true in this case is anything that's not an NA. And I did that for both of the columns in my data set. So I said filter is not NA departure delay, and is not NA wind gusts. And then I plotted, or I piped this right into the ggplot. With the aesthetics, X is the wind gusts, Y is the departure delay, with G on point and G on smooth. Because the data are, or because data is the first argument of ggplot, you can just pipe them right into the plot. And this is often how I produce reports and things. Okay, that's a great question. It was, why did I select all of these variables when I only needed to keep 2 of them? In order to make the comparison about departure delays and wind gusts, I needed to have the exact time that the wind gusts and the departures were matched. So in one data set, it's just the weather. And in the other data set, it's just the flights. And so if I want to know whether or not the wind was related to the departure delays, they have to be at the exact same place at the same time. And so I match on all of those things, but then I only want the column from the flights data of the departure delays, and I only want the column from the weather of wind gusts. Yes, because inner join's going to keep only the rows and columns that match. Right? I always have to check the thing. I'm sorry if I said that wrong.
No, I have to think about it, but I think that makes sense.
It'll make more sense once you see all the data frames and all of the matching columns and what you can join. So what do we got? It looks like there's 1,200 mile/hour winds and no departure. So sometimes it's great to make a plot because you'll find out that somebody put the wrong thing in the data. Because clearly there's not 1,200 mile/hour winds and they just took off. Those things don't coexist. And so I added a line in the filter that says, and wind gusts that are less than 250 miles per hour, because I don't know. I'm 99% sure that that's been fixed in the data sets, but I'm not exactly sure. I also removed the geom point, which didn't seem like it's going to be that useful, to focus on the average trend produced by the geom smooth. And so then we get this delightful little graph, which seems to suggest, one, that as wind gusts go up in miles per hour, that departures delays seem to also go up. And also, seeing as the confidence band seems to get larger, we don't have very many cases out here. That's what that tells me.
On that first one, our graphs are like concentrated just like in the x-axis of 0 to 100.
Mhm.
We don't see the outliers.
Okay.
It's the next slide now. I'm doing this with smart. It's just showing my plots.
I'm not exactly sure what you mean. So that you're saying you're not getting these observations out here.
Yeah, it just looks like it's it's just cut off and only showing but I can.
Right. I feel like that's what I was saying. Like, I'm pretty sure this is fixed in the data. Like, this was an error when they created this data set, but I don't think it exists anymore if you just install it.
Oh, I see that.
So for your homework, you're going to be tinkering with the NYC Flights 13 data. And I have a couple of suggestions of possible questions to investigate if you are unsure. Things like, what are the names of the most common destination airports? Which airlines fly from New York City to your home city? Is there a relationship between departure delays and precipitation? What is the distribution of departure times from flights leaving New York City over a 24-hour period? Are especially late or early arrivals or departures to some regions or for some airlines? A word of warning, though, the flights data has 336,776 rows. So if you do a sloppy join, you can end up with many matches per observation and have the data explode in size. and this will crash your computer. Uh, so just be ready for that. That might happen. Don't just run it again if that happens to you. The reason is because R saves information in your RAM. And if you don't have that much RAM and things get exponentially large, your computer will get slow. It'll happen. It happens every year. Homework 3. So you're going to pick something to look at in the NYC Flights 13 data, write up a markdown file showing your investigation, upload both the markdown and the HTML file to Canvas. You must use at least once the mutate function, the summarize function, the group by function, and any of the joins that are on that original slide. Include at least one nicely formatted plot in ggplot2 and one table in Panda. In plots and tables, use nice variable names, maybe give spaces a try, and rounded values, so less than or equal to 3 digits. This time, include all of your code in the output document, so echo equals true. Using comments and line breaks, separating commands so that it is clear to your peer reviewer what you were doing or what you were trying to do. You must write up your observations briefly in words as well. Note, if you want to see the NYC Flights 13 data frames in the environment, you will need to load each one. And that's it. Do you have any other questions? Great. I'll see y'all on Monday, maybe virtually and with less teeth.
You're getting them out on Friday?
I am.
I would say, yeah, probably.
Okay. I'm getting my teeth out. I'm getting my wisdom teeth out.
Oh,
Yeah.
eat pineapple.
Eat pineapple before?
Yeah.
Interesting. Okay.